Hey, folks, welcome back to EarthSky. And today we are going back in time. We are going all the way back in time to this thing right here, whatever it might be. And our guest is going to explain to us why we have to start here. We are going to talk about the rate of the expanding universe, what it can tell us maybe about its size and its age, and answering those critical questions is probably the foremost expert in cosmology working today, Wendy Freedman. She's an astrophysicist and astronomer at the University of Chicago, and her latest work could help us solve a string of lingering questions. Wendy, welcome. Thank you so much for being here. Proud to have you.
Oh, very pleased to join you. Thank you for having me.
Yeah, thank you. Thank you. So last month, you and your team, you're working at the Chicago Carnegie Hubble program. You released a refinement of the value for the expansion rate of the universe, and that's a number known as the Hubble constant. Can you tell us what the Hubble constant is?
The Hubble constant is the quantity that tells us how fast the universe is expanding today. And so, yeah, that's a simple definition.
That is the very simple definition. Okay. So we've been trying to refine the value of the Hubble constant, but there's been a debate, right? What exactly is the debate and where does it originate?
Well, it actually goes far back. To Edwin Hubble, of course, made the discovery that our universe is expanding, and the Hubble constant is named after him, and it's the current rate at which it's expanding. And Hubble measured a value of 500 kilometers per second per megaparsec. Those are the units that we measure the expansion rate in. But it became clear that eventually that the calibration, the measurement was an error, and that the Hubble constant was not nearly as large as Hubble had anticipated that it would be. And so from the value of 500, it came down to about 250 in the 1950s. And then in the 1970s, there were many people trying to measure the Hubble constant, and they were getting values between 50 and 100. So there was a factor of 2 uncertainty in the Hubble constant. For many, many decades, it persisted. And it was actually our group, the key project with the Hubble Space Telescope, that resolved that factor of 2 debate. And we measured a value of 72 in these same units of kilometers per second per megaparsec. And that was an uncertainty attached to that was about 10%. That was our goal, to make a measurement of the expansion rate to an accuracy of 10%. And we did that, and we thought we were done, or I thought I was done. I was never going to work on the Hubble constant again because we'd solved this factor of 2. But in recent days, recent decade, in fact, there's another measurement now that is made with measuring very small fluctuations in the temperature of the background radiation from the Big Bang. And that method gives a value of the Hubble constant of 67. And the local measurements are tending to be higher. They're tending between 70 or 73 kilometers per second per megaparsec. And so if we're at the high end of that range, then the difference between 67 and 73, if the uncertainties are small enough, they would be indicating that maybe there's something we don't yet understand about how the universe has been evolving. And so that's the current tension, which we can talk more about, and which we're actively engaged in trying to understand that today.
So the tension is the difference between the result we get from measuring cosmic microwave background radiation versus the technique that you used. What is the technique that you used in 2001 and then again for the latest work?
Yeah, so what we're doing is measuring the local value of the Hubble constant. So galaxies around us, we're measuring the distances to those galaxies in the way that Edwin Hubble originally did, and we need to know the velocities of those galaxies, how fast they're moving away from us, and if we can measure those distances accurately, as Hubble was able to demonstrate, so what his original discovery was that if you plot the velocity of a galaxy versus the distance to that galaxy, those are correlated. And the slope of that relation is what we now call the Hubble constant. So galaxies that are farther away from us are moving away faster. Galaxies that are somewhat closer, they're moving away from us, but they're moving at a slower rate. And so the velocities turn out to be not a difficult quantity to measure. We're just simply measuring displacement of lines in spectra that are due to atomic or molecular transitions in the atmospheres of stars. And we can compare those to laboratory measurements, and that's a straightforward measurement. The distances, however, have turned out to be much more challenging. And that's why really the difference in what Hubble measured and what we are measuring today. And so if you think about it, we're trying to measure these vast, vast distances, and we're using stars, and we're trying to use properties of stars so that we can infer how bright are those stars, and then use the inverse square law of light that then tells us the distance. So there was yeah.
What is the inverse square law for people who may not know what that?
So the intensity of light, so people would be familiar, if you look at a light in the distance, look at a lamppost in the distance, if you look farther and farther at more distant lampposts, they're fainter. And the intensity of that light falls off as 1 over the distance squared. That's what we mean by the inverse square.
So if we know how bright one of these stars is, then we know how far it is away, right? And Hubble, that's what Hubble did. Right, as he looked at after he figured out that there's more than one galaxy in the universe, he then took a look to see how far they were away, and he found what you're telling us about, right? And then you, building on his work, came up with a number, but you've done it again, right? That's what you've done now, is you have a new number, and that number is 70.39 with 3 error factors. What does that mean, and what's an error factor? Can you explain what you've come up with, and what does that tell us? What does it tell us about our universe?
Yeah, so when we're making these measurements, we want to understand what are the uncertainties in the measurement, right? So there are different kinds of uncertainties or factors in these errors. And so, for example, if we take a coin and we flip it many, many times, how many times will it be heads, how many times will it be tails? And if it's, not a weighted coin, something, 50% of the time it'll be heads and 50% of the time it will be tails. And so the more times we make a measurement like that, the closer we're going to get to actually having half and half, right? If you do it a few times only, then you might get more heads than tails and think, okay, that's not what you expect. But the more times you do it, the more accurately you can bring down that uncertainty. We call that a statistical uncertainty, and it has to do with the number of measurements that you make. There are other kinds of uncertainties, and those, no matter how many times you make the measurement, you're never going to get close to the actual value of the quantity you're trying to measure. So, for example, when we are measuring these stars, and we can talk about the kinds of stars that we use in a moment, what we have to think about is there are dust grains in the medium, the interstellar medium, between us and the stars that we're trying to measure. So these stars are forming out of dust and gas, and the dust grains are being spewed out of the atmospheres of stars at the ends of their lives. But the dust grains themselves are going to scatter a photon of light that comes in our direction, either scatter or absorb it. So what's the effect of that? It's going to make your star look fainter because we're not going to see the photon that is absorbed or scattered out of our line of sight by the dust. And it also has the effect of making the object look redder. because it is more effective at scattering the blue light than the red light. And that turns out to be important when we talk about the James Webb Space Telescope, the fact that it reddens the stars that we're looking at. And so again, we can make the measurements over and over and over to a star, measure how bright it is, but if we're not able to correct for the presence of this dust, say, or the presence of what we call metals in the atmospheres of stars, then we won't get the right answer. We have to find a way to correct for those things. And so those are called systematic errors. They're not statistical in the sense that you can make more and more measurements and be more accurate. They're going to be there unless we find a way to overcome them. And our third factor that you noticed, we added that because there's a new uncertainty that has popped up, which is the uncertainty in measurement of the nearby supernovae that we tie our Hubble constant in to look at the expansion of the universe, where the presence of other galaxies is not adding noise to the measurement. And what I mean by that is galaxies actually tend to like to be near other galaxies. They're like people, they don't like to be alone. And so they're inducing motions in nearby galaxies just because of the gravitational interaction between them. And as we said, the velocity of a galaxy is larger when you are at a greater distance. So these kinds of interactions are a smaller proportion of the overall velocity of galaxies that are expanding in the more distant universe. So we use bright supernovae to help us get out into what we call the Hubble flow, where we don't have to worry about these gravitational interactions. And so we just isolated that because that's a place now where I think we need to focus our attention if we're going to get at this tension now.
Okay.
And understand, is it real? So that's the question before us. So when we looked at the factor of two debate that was in the 70s, 80s, and 90s, it turned out to be these kinds of issues like the dust and the calibration, how, measuring how bright a star actually is. But now, as the measurements have gotten more accurate, we can start to ask the question, is this a real difference? And if it's a real difference, what we're seeing in the background radiation and the Hubble constant that is inferred from those measurements, and what we're measuring locally. So here we are coming from a high redshift universe, and we're measuring the low redshift universe, and they're not matching. And that's a problem. So each of those is supposed to be telling you about the same quantity, the current expansion rate. And the distant measurement from the microwave background can be fit by what we call the standard model of cosmology, which tells you how much matter there is in the universe, including dark matter, and can be fit, this model, the data from the microwave background could be fit with only 6 parameters. And then that's a very prescriptive model. It tells you exactly how the universe should be evolving and what the expansion rate would be today. And they are not matching. If the microwave background is giving 67 and the Cepheids, which we haven't yet talked about, but these are the stars that Hubble used, they're the ones we use for the key project, that method is giving a higher value of the Hubble constant. So I should have switched my hands, but but
we get it.
But the basic idea is those should give you a number that is consistent, and they don't. And so the question becomes, is this something that's telling us about the property of the universe, something we don't yet understand, which would be extremely exciting? Or are there still measurement uncertainties similar to the kinds of things that we've had to deal with now for a century since Hubble started measuring distances to galaxies? So that's the issue before us, and we're trying to improve the accuracy and see whether or not we can determine whether the current standard model is the correct one, which is also an important thing to do, to actually be able to confirm that that's the correct model, because it's also a model that we don't yet understand the constituents of the universe, in the sense that There's a lot more matter in the universe than we knew about until recent decades. It's dark. It's of a different form than the ordinary matter that you and I are made out of, and everything around us, and also this dark energy, which is, now we understand, 2/3 of the overall energy mass density of the universe. But we don't yet know what the dark matter is. People have been looking for this for decades now, trying to understand what the dark matter particle might be. And we don't yet, at a fundamental physics level, understand the dark energy. So lots of mysteries in cosmology right now, and potentially a new one, which is the Hubble tension that may be signaling yet more that we didn't know about before.
Well, I'm feeling very tense. I can tell you that right now. So you did come up with a number that is much closer to the cosmic microwave background derived number.
Yeah, we did.
What does your finding tell us, that rate of expansion, the Hubble constant? Does it have any implications for how the universe began, how it will end? I mean, is the universe going to stop expanding and fall back on itself? Will it go? What's this tell us about everything? Literally everything.
Yeah, this is one of the interesting things about this new quantity, this dark energy that in the year 1999-2000, energy evidence that the universe is not only expanding, but it's actually speeding up in its expansion. The universe is accelerating, and that's what gave rise to this idea of dark energy. And we don't know, as I was saying, we don't yet understand what has given rise to this dark energy. And so that leaves us with a puzzle. So most of the observations to date suggest that the dark energy is consistent with something called the cosmological constant, which is a quantity that Albert Einstein first recognized when he was coming up with his general theory of relativity, that the universe would not be static. That is, it would either be expanding or contracting, but it couldn't be static. And so he introduced a term, just a mathematical term, to force the universe to be static. And he had, of course, consulted with astronomers of the day to see whether there was any evidence of expansion, but Hubble hadn't yet discovered galaxies. And so astronomers knew of stars. The stars that they were measuring were in our Milky Way, but these faint so-called nebulae had not yet been identified as objects that were like our own Milky Way galaxy, only farther away. And that's what Edwin Hubble discovered. And so this cosmological constant, when Hubble then discovered the expansion, Einstein reputedly said that this was the worst blunder of his life, that he had missed the opportunity to predict the expansion. He knew the universe had to be doing something, and it turned out the universe couldn't be stable. So he was trying to make it static, but it wouldn't have mattered, literally, if somebody had sneezed, it couldn't have stayed without being in motion. So the interesting thing is that most of the observations to date are consistent with Einstein's cosmological constant, even though it's certainly allowed within general relativity, a repulsive form of gravity. But there is some hint that maybe this cosmological constant, this dark energy, might not have the same value over time, could be evolving with time. And then we because we don't know about the nature of the dark energy, we don't know what the ultimate fate will be, because we don't know what this thing is that's causing the acceleration right now. Until we have a good fundamental physics understanding of it, we've lost the ability to predict what the fate of the universe will be.
That's not good. That's a bad position for you to be in as a cosmologist, or as anybody who happens to be living in our universe, because this has some implications for where we're headed.
It does, but fortunately, none of us will be here. It's far in the future.
Yeah, we won't be around
But
for
it
that.
is
I'm
interesting
sorry.
because, in fact, we happen to be living at a time where there are all these galaxies around. But if the universe keeps speeding up in its expansion, then those galaxies are going to recede from us, so that eventually they'll be out of our horizon. That is, they'll be far enough away that light won't have had enough time to travel, given the age of the universe, to reach us. And so there will be a time in the universe, 60 billion years or so from now, when we won't see most of the galaxies. They will have receded out of our horizon if it continues to accelerate in the way that we are seeing it today.
Any entity living at that time would have no idea that the rest of the universe exists. There's no
That's
way
right.
that they can communicate via light. It's too slow. Okay, so as long as we're bending minds, here's another mind bender. We're talking about an expanding universe. But to the common mind, to my common mind, in fact, that implies growing into something, but that is not right, is it? What the heck is going on here?
Well, what's happening is general relativity describes is that space itself is being created. That is, when we think of the Big Bang and we think of an explosion, our natural tendency is to think of something like a bomb with a center. Pieces fly out from the center, and it's expanding into something. But in this case, the universe itself is being created. Space is being created as the universe is expanding, and galaxies are being pulled along with the expansion of space. That is, they're not moving relative to space. They're actually participating in the overall expansion. And it's a hard concept. One of the ways that Stephen Hawking described it was, if you're asking what is the universe expanding into, it's like asking what is north of the North Pole. I mean, it's not a question that makes sense, right? It's the universe itself is space itself is being created as the universe is expanding. It's not expanding into anything.
It's just expanding. It is infinite but unbounded. Is that, or is it the other way around? And that doesn't even make sense to me. I'm sorry. Let's ignore that.
And as I said, we don't know what the ultimate fate will be, because if this dark energy is evolving with time, in principle, at least, it could start contracting again. We don't know at this point.
Why are all these questions so hard to answer? You spent your life doing this. What is it that we can't get into our heads to make this work?
Well, just think of what we've learned literally in just the last century. I mean, we continue to push the boundaries, the frontier of science, and the more we push, the more we have learned. So, just over a century ago, we thought the Milky Way galaxy was it, and stars were the constituents, and it all made sense. And then now we understand that we're living in a dynamic universe that's evolving with time. It's expanding, and now we know it's accelerating. And not only is there the matter that we know and love, but there's 6 times more matter in a form that we still don't understand what it is. And then there's even more of this dark energy. So we've learned an enormous amount, but we're talking about a vast, the universe itself. It's continues to provide mysteries that we're trying to understand.
And beautiful, fascinating mysteries at that. We have gone a very long time here. Should we continue or should we not? I am so fascinated, but I don't want to take up your time, Wendy.
The only thing I wonder is whether you want to have any discussion of Henrietta Leavitt and Hubble and Cepheids and red giant red stars. But if you're happy with where we are, I'm
happy either way. And so we could talk about this woman right here. This is Henrietta Swan Leavitt, and I would like to talk to her about her. I would like you to talk about her, actually. Tell us who she is and what she did and how that got us here.
Henrietta Swan Leavitt, everything that we have done in modern cosmology rests on the discovery made by Henrietta Swan Leavitt, who she was an astronomer working at the Harvard College Observatory. And she was interested in stars that were in a cloud called the Magellanic Clouds. These are objects you can actually see by eye if you go to the southern hemisphere, the small and the large Magellanic Cloud. And what she discovered was that there were stars embedded in this sort of nebulous object, big nebulous object, that were changing their brightness over time. And what she found was, so these stars would increase in their brightness very slowly and rapidly, they would increase rapidly and then decrease in their brightness very slowly over time. So like a sawtooth shape to them. And what she found was that the rate at which they went through this light variation was proportional to how bright the star is, in the sense that the rapid changes were in fainter stars and the slower changes were in brighter stars. And so this is the basis of what we now call the period luminosity relation, this relation between the brightness of the star and the rate at which it's varying. And that turned out to provide the key to how we measure distances. So if you think of it, if you look up at the night sky, you see things in 2 dimensions, but you don't know that third dimension of the distance. And astronomers had no way of doing that except for the very, very, very nearest stars, and for which they could use geometry. And so this relationship is what Edwin Hubble then used when he found these stars again in what were at the time called nebulae. And he was able to show, and in fact, there was a debate at that time in the 1920s that over the question of whether the Milky Way galaxy was the entire extent of the universe, or whether there could be other so-called island universes similar to the Milky Way, but outside of the Milky Way itself. And Edwin Hubble was able to resolve that question by finding Cepheid variables in these nebulae, and to show that they were actually at much greater distances, and then combined with measurements of the velocity, which he then plotted the velocity versus distance, he was able to show that there was this correlation between how fast is a galaxy moving and how far away is it from us. And together with Einstein's general theory of relativity, that is what led to our picture. Things are expanding now, then they must have been closer together in the past. And you extrapolate back in time, and you come to this idea that the universe would have been much denser, much hotter, and what gave rise to the picture we now have of a Big Bang universe that started with this colossal explosion and has been expanding ever since. And so, we use the period luminosity, Hubble used the period luminosity relation. We used it for the Key project. We use it today for Cepheids. It's a remarkable discovery by Henrietta Leavitt, who didn't live long enough to see the implications of her own results. But in 2008, we named the PL relation, the period luminosity relation, the Leavitt law, because there's so many. There's a Hubble law, Hubble constant, Hubble galaxies. There's so many Hubble things, but she was not recognized and unknown to younger astronomers. She kind of disappeared from history, but
well, let's get her back on the stage because she deserved it. We are standing on her shoulders.
Yeah, very much so, all of us. And she, in fact, was nominated for a Nobel Prize, but she had died before that could be awarded, if that would have happened. Today, they don't award it posthumously.
They do not. They do not. Okay, so, but you didn't just look at Cepheid variables. You looked at 3 different varieties of stars. And it was through technological development that you were able to do that. Tell us what it is that's new. What did you do this time around you weren't able to do in the 2001 work?
So in the 2001 work, we used the Hubble Space Telescope and we measured the same Cepheid variables. We also measured stars called red giant branch stars, but they weren't the focus of the key project. They were a consistency check on the Cepheids. So we found, based on the Cepheid calibration, using 5 other methods to measure the Hubble flow, that the Hubble constant was 72 with an uncertainty of 10%. Since that time, we now have other distance indicators that we have developed in addition to the Cepheids, including the red giants and a new type of distance indicator using carbon stars that are redder than the Cepheids. And what we now have is this amazing new facility in the James Webb Space Telescope, which was launched in 2021. I hope I'm getting that date right.
I'd have to look.
Christmas Day. And this is a giant telescope. It's much bigger than Hubble. The primary mirror is 6.5 meters compared to Hubble's 2.5 meter telescope mirror. And it's sensitive to infrared radiation. And so these dust grains that we worry about that are absorbing and scattering light that's coming to us from these stars that we're measuring, the infrared radiation has a much longer wavelength than the optical radiation that Hubble is sensitive to. And so the infrared radiation essentially passes through the dust. So there's much less of a systematic effect when you observe in the infrared. And it's also a bigger telescope, so it's more sensitive, and it has higher resolution. So what I mean by that is the ability to see very clear detail, like putting on eyeglasses. And so our program now is to use the James Webb Space Telescope to use 3 different indicators, the Cepheids, the tip of the red giant branch, and these carbon stars, and measure the distances to the same galaxies so we can compare them. How well do they agree? And that's new because in most cases, people have measured using one technique in this galaxy, another technique in another galaxy, and it's really not possible to compare and understand, again, what kinds of systematics could be affecting the different methods. And using these 3 allows us to see in great detail how well do they agree. So we didn't know, would they all be different? Would they all agree? Would 2 agree and 1 not agree? And to our pleasant surprise, they're all agreeing very well. And that's new in the distance scale. We have not had that ability to make that comparison with methods that are this precise before.
Okay, so what next? Where do we go from here? How do we move to the next stage on this? How do we up our game?
There are several things that I think need to happen. We first need to increase the sample again so that the statistical uncertainty decreases. We just got time, my collaborator Barry Bedore and I got time to use these new carbon stars to measure the distance to a cluster called the Coma cluster, which is 100 megaparsecs away, over 300 million light years away. So we don't have to use supernovae. We can skip the stage of going into the Hubble flow with these bright supernovae. So that will be very interesting because, as I mentioned, the supernovae, at this point, we're needing to understand what the uncertainties are there. I think the other thing that needs to happen is we need different methods that have nothing to do with measuring the brightnesses of stars, because one of the remaining uncertainties is how well can we calibrate the absolute brightness of these stars. So we can measure relative distances very easily by comparing how bright an object, a star or a galaxy is at a given distance compared to another. But at some point you have to attach an absolute calibration, how bright in watts per per square meter that gives you an actual absolute calibration. And so I think there are techniques, for example, using gravitational waves. There's a technique called gravitational wave sirens. And these measure as neutron stars, binaries coalesce. You can measure that signal, and it allows you to measure the distance that's quite independent of any flux calibration. Now, you also still need a velocity, and you need a sample of objects, which unfortunately these neutron star binaries turn out to be very rare. There's only one that's been well observed so far. But it's that kind of thing that I think is going to be very important in the future. If the community ultimately is to say, okay, we've nailed the Hubble constant, we're going to have to do this in a way that is based on very different kinds of physics, which, I think our project is a first stab at using Cepheids, tip of the red giant branch, and carbon stars. But again, you'd like other methods that are, again, completely independent. And I think at this point, the measurements of the fluctuations in the temperature and also the polarization of the microwave background light and the fit to the standard model, that they're making those measurements and inferring the Hubble constant at a precision that is better than 1%. And so there's the Planck satellite that's made those measurements. There are 2 ground-based experiments, one at the South Pole and one in the Atacama Desert, that are agreeing very well with those measurements from the Planck satellite, the European satellite. And so we haven't quite converged in the nearby universe at the same level of precision. And so I think, as various groups are continuing to refine their techniques, and I think the issue before all of us is to understand the systematic errors again. It's not statistics, it's systematics. Have we overcome them? But the microwave background measurements have set the bar very high. That is, they're better than 1% precision. We're not there yet in the local universe. So various estimates are, from 1 to 3%, in some cases 4 or 5%. But I don't believe that we yet have the accuracy to be claiming 1%. There are just too many moving pieces in the distance scale, in the supernova measurements, and the types of corrections that need to be made. I don't yet believe that we have the confidence to say that this is, at a 5 sigma level, that is a 1 in 2 million chance that this is real. I think we have more work ahead of us. But the exciting thing is that it's a lot more work. But this is an empirical question. We will get to the bottom of it, but it's hard. It is a challenge. But it is. But not to be pessimistic. When we think of where we were just a couple of decades ago, we were talking about a factor of 2 uncertainty in the distances. When I started my career, that's where we were. And then with the Hubble Space Telescope, we got to 10%. And I'd say we're at a few percent now. We're not at 1%. And that will take us a while longer to get there. But we're making enormous progress. And I think that will continue. So, yeah, I'm optimistic.
That's like the difference between knowing whether you're 50 or 100 versus knowing whether you're 99 or 100. That's an important thing to know about where you're going. Wendy, so incredible. You got a lot of work to do, so I'm going to let you get back to it.
Thank you. I appreciate that.
Oh, I appreciate you being here so much. This has been a true eye-opening conversation, and I hope to continue it with you when you get some new stuff. Incredible. Thank you. If you want to hang around backstage, and we'll chat for a second, and you can get back to work.
Okay, we'll do.
Okay, thanks. Hey, folks, wasn't that great? Oh, man, we will be back tomorrow. Sorry to keep you so long today. We have an accidental planetarium discovery that happened when they were doing a show in New York City. It's going to be another great talk. That'll be at 17:15 Universal Time. Same as we do every single weekday. We are here every weekday. You should subscribe. You don't want to miss this stuff. Look how good that was. And give us a like too. Come visit us at earthsky.org. See you soon, my friends. One Earth, one sky, EarthSky.